Hi, my name is Jim, and what we want to do today is look at simplified formula for finding the gain of inverting and non-inverting and summing amplifiers. This was alluded to in the previous video but not explicitly pointed out. So let us start with the inverting amplifier first, which we see on the top here. And what our gain formula is the negative value of R sub F, which stands for the feedback resistor, divided by R sub I, which is the input resistor. And these are common subscripts that are used in op-amp circuits. They don't have to be RF and RI, they can be something else. So if we take a look at this and we see that we have an input here of 0.5 volts, the gain equation for this is the ratio of negative R sub F over R sub I, and then multiplying that out, we see that we have negative 5 volts as an output. So positive input voltage times a negative gain is going to be giving us a negative output. Now, if this were to be an AC signal, all this negative would mean is that the output is 180 degrees out of phase with the input, nothing more than that. Another question we have is this RX guy that's sitting in the non-inverting input, and since our bias currents are relatively low, we can sort of disregard them in many applications. But if we're dealing with a bipolar operational amplifier and we want to minimize bias current errors, what we want to have is the non-inverting terminal looking into the same resistance as the inverting terminal. So to find out what this is all you do is take the other two resistances which attach to this and combine them in parallel, and that would give us is 909 ohms. Now under this circumstance, the input error due to bias current would be 0, but we would still have an I sub IO, and that would be the actual difference in bias currents, which we can't really control. And we don't really know which one can be greater if one is greater. So we can minimize bias current errors by doing this. Now in JFET or CMOS op-amps, this is virtually not even an issue because the bias current is extremely low. Remember that this is bipolar. You have base currents flowing. So let's take a look at our next circuit here, and this is a non-inverting input. We're feeding V in here into our terminal, and the gain equation for this is very similar. It is the ratio of RF over I plus 1, and do note that there's not a negative sign in this. So if we were to feed in here an input of 0.5 volts, what we would see is that we would have a gain of the amplifier of 11. So positive 5 volts times a positive 11 means that the output voltage on this would be 5.5 volts. Again, since these values haven't changed, is Rx would be 909 ohms. Now, that means if we were really worried about this, is that in the path of the non-inverting input, we would have Rx and assume that the driving impedance is 0 ohms. So this would be added to the input impedance of whatever circuit's driving it. It was another operation amplifier. For all practical purposes, we can consider that to be 0 ohms. Now let's take a look at an inverting summer. And here we have two different inputs which are being added together, hence it's called a summer. And what we can do on this is, since we're operating in a linear mode, is kind of figure out what the gain of one is, figure out what the gain of the second is, and add them together. So this is a form of superposition. So let's take a look at the first input. It's 1 volt, and the gain on this is going to be negative 10K divided by 1K right here, and then we're simply going to add to that the gain of the other input, which is negative 2 volts, and the gain of this stage is going to be 10K divided by 5K, and this ends up being 2. So what we have here, if we multiply this out, is negative 10. If we multiply this out, we get plus 4, adding these together at the output here, what we would have would be a negative 6 volts. So if these were AC voltages of the same frequency, as we'd be doing a subtract operation. If they were AC voltages of different frequency, we would see peaks which are higher than this depending upon the instantaneous value of that. Spectrally, if we looked at a spectrum analyzer of the two, coming out of this first output we would see 10 volts, and coming out of the second output we would see 4 volts. And I'm showing these at different frequencies. Maybe 4 up here actually and 10 here. So the only way we could actually determine with an AC source what the output would be to transfer this into the frequency domain, because if the frequencies aren't the same, you're going to add up and possibly have a waveform that looks like this. Very, very hard to determine frequency components of two sinusoids which are not the same frequency in the time domain. So we have to be using the FFT function to actually analyze how the amplifier is handling each individual frequency. Again, if it were AC. Now, if we take a look at a non-inverting summer, things get a little bit difficult. Unfortunately, and I've got 3 inputs here, VN didn't even bother to specify at 5 volts and negative 2 volts. And the problem with this is we absolutely have to know what this voltage is right here. We cannot use the non-inverting gain on this, add it to the non-inverting gain on this, add it to the inverting gain on that to figure it out. Now here's why. What if this resistor were 1 ohm? What would that do to the negative 2 volts as far as what the actual op-amp is going to see? Going to destroy. It's going to be much, much, much less. Let alone the fact that this source is also seeing this 1K to ground, because the internal impedance of 5 volts is 0 volts. So even if we don't have 1 ohm here, we end up with kind of a complex mess where the 1K would have to be placed in parallel with this 1K, because this effectively looks like a ground to this source. So unfortunately, in this type of circuit, the negative 2 volts never gets to be here because of this resistor and this resistor. So the only thing we can do is break this out, and to make it simpler, and remembering that our op-amp here is, for all practical purposes, so we can consider it an open circuit, and then we have to solve for this voltage right here by using circuit analysis techniques. Once we get that, because of virtual short, we transfer this up here, and then we can figure out by pushing currents. Or, if we get it here, now we can use the 2 simplified equations. So in this case, if I let this be 10K and this be say 5K, what my V out would look like for the first input would be V1 Vn times negative 10K divided by 5K plus, and we'll say, for example, that this input is 0.5 volts. And that would be the summation of these two as determined by this network. So we would have 0.5 volts times 1 plus 10K divided by 5K. And since I don't have a value for Vn, I can't actually determine what the output would be. But what you can see here is when you get this voltage, you do not have to push currents through the inverting side of the circuit. But you have to know what that voltage is to solve the problem. Now, if I've only drawn 2 resistors here, some of our problems have 3 resistors. Always remember if you're using superposition, which I believe to be the easiest way, is you make one source active and ground the other sources. If he's the active source, this guy is in parallel with him. 5 volt internal resistance is 0 ohms. If this is active, then we have the 2K in parallel with 1K. Find out what the voltage is here at this node on the non-inverting terminal of the op-amp. So this kind of problem is unfortunately more difficult to solve than it would be if we were only using the inverting summer. So that'll conclude on this, and thank you for watching.